Hello, chemistry students. Yesterday we talked a little bit about Avogadro's principle, and so remember Avogadro's principle states that as long as the gases are at the same pressure, temperature, and volume, regardless of what the gases are, they're going to have the same number of particles, which now we associate with Avogadro's number 6.02 times 10 to the 23rd. We also talked about a fifth gas law, which is called the ideal gas law, which deals with not only pressure and volume and temperature, but it also introduces the moles, the amount of stuff that we have. And so we talked about Pivnerts, and so PV equals nRT, and so we're going to talk a little bit more about this today. We'll also do a problem, and so then you can try some out then for homework tonight. All right. The number of moles is a fourth variable that can be used to describe a gas. The ideal gas law will relate the pressure, the volume, the temperature in Kelvin, and the moles together with, of course, our Pivnert equation. So P times V equals nRT. The R, as we talked about yesterday, is called the ideal gas constant. If you remember from last chapter when we're looking at states of matter, you'll recall that gases are measured in a variety of different types of pressure. And so there are three different gas constants that all depend upon what type of measurement you're making your pressure in. And so notice that in this first gas constant, we're looking at pressure in terms of atmosphere, and so this is going to be 0.0821 liter atmospheres per mole K. If we're, however, looking at pressure in terms of kilopascals, kPa, the gas constant then is 8.314 liters kPa over mole K. If, however, we're looking at pressure in terms of millimeters of mercury, we have yet another gas equation. This is going to be 62.4 liters millimeters of mercury per mole K. And so before you turn this off, and before you freak out, I will tell you that I will provide you all three of these constants on the test, so please do not have to feel like you have to memorize this. I also wanted to point out, again, depending upon what the pressure measurement is in, that will then tell you which of these three gas constants to use. Because if you look at the other units, the liters is the same, the mole is the same, and of course temperature is in Kelvin, that's the same. So depending upon the measurement of pressure will then determine exactly what's the gas constant that you'll use. But again, don't panic. I would give you these three constants on the test, and so your job then is to pick which of these three would be the correct one, therefore, to use to then solve a problem. And so let us go ahead and take a look now at real versus ideal gases. And so an ideal gas is one whose particles, if you remember from before, take up no space and there are no interactive intermolecular attractive forces between them. The real world, as we know, is never as simple as that. The real world, there's no gas that is truly ideal because we do know that particles of gases, even though they're very, very small, when we have a large collection of them, they are going to take up some volume, and we do know that they will show some interactions. And so, despite this, most gases will behave like ideal gases at many of the common temperature and pressure levels. And so I do want to point out there is a real gas law that accommodates for both the space and intermolecular attractive forces. However, in this class, you will not need to worry about that. And so I will save that then for an advanced class in college. But for right now, we're going to focus on ideal gases, and therefore we're going to focus on Pivnert. And so let's go ahead now and take a look at an example. And so let us calculate the number of moles of gas contained in a 3-liter vessel at 300 K and 1.50 atmosphere of pressure. All right, and so you'll see that we're looking for what? We're looking for the number of moles. We're given the liters. Our temperature, fortunately, is already in Kelvin, so we don't have to go ahead through that conversion. And we're told that the pressure is 1.50 atmospheres. So again, the pressure unit is important because that tells us which of the three gas constants that we need in order to do this. And so I'm going to go ahead and turn your attention toward the board. And so here again is our ideal gas law. And so we have Pivnert. So remember, P stands for pressure, V is for volume, N is for moles, R is the gas constant, and T is the temperature in Kelvin. Notice that in this problem, we're looking for moles. And so to make my life easier, and make your lives hopefully easier, I'm going to go ahead, I'm going to move the RT to the other side. So remember, the opposite of multiplication is in fact division. And so if we want to solve just for N, we can say that N equals PV divided by RT. And so all I did was I divided both of these sides by RT, and so that I can get N by itself, because that is what I'm interested in solving for. So I'm going to go ahead and write that N equals PV over RT. Of course, you could go ahead and plug in the constants or the numbers that they are provided for you, but for myself, because I'm looking for N, I go ahead and set this up first so that way it makes the calculations a little bit easier. All right, remember in the problem, we're told that the pressure was 1.50 atmosphere, so we can say N equals 1.50 atmosphere. The volume of our gas, we're told, is in 3.0 liters, so we'll go ahead and we'll put that also on the top. Remember now that R is our gas constant, and so our gas constant depends upon the pressure unit. Notice that our pressure unit in this case is atmosphere, and so in the case of atmosphere, if you'll recall, if we look over here back to our board over here, you will see that in terms of atmosphere, our gas constant is going to be 0.0821. And so that's going to be for that. So we're going to have to use this constant in this problem because, again, the pressure is being measured in terms of atmosphere. And so if it was measured in terms of kPa or millimeters of mercury, we would have to use these other two gas constants accordingly. But however, we're going to use this first one because, again, it is in terms of atmosphere. So it's going to be 0.0821. So we're going to go ahead and put that over here. And so we have 0.0821 liter atmospheres per mole K. And so I realize that this is kind of a funky unit, but in order for everything to balance out, we do have to have this unit. And so our temperature, we're told, of this gas was at 300 Kelvin. So we were told that it was at 300 Kelvin. It's already been converted for us, so we don't have to go ahead and do the additional step of converting from Celsius to Kelvin. We know that it's 300 K, so we're going to go ahead and put the 300 K in here. Notice again that we're solving for moles, and so moles in the ideal gas law is represented by a lowercase n. So again, the n is the moles. And so to solve this problem, we need to take 1.50 atmospheres times 3.0 liters divided by 0.0821 liter atmospheres per mole K, and then divide that also by 300 K. And so if you look, you'll see that the atmospheres cancel out, the liters cancel out, the Ks cancel out, and since this mole is already under a division sign, it's going to be brought up to the top. So our measurement is going to be in terms of mole. And so I'm going to go ahead and plug this into my calculator. And so when I go ahead and do that, I'm going to go ahead and I'm going to take 1.50. I'm going to multiply that by 3.0 on the top, and then I'll divide by 0.0821. And then also I'm going to divide that by 300. And so when I go ahead and I do the math in my calculator, I'm going to end up getting roughly 0.18 mole. And so I know that for this particular gas that I have 0.18 mole of whatever that might be. All right. And so I will tell you that, as you can expect on the test, that there will be a problem that involves the ideal gas law. And so again, I just want to remind you that you will have to be given 3 out of the 4 of these variables. And so again, remember, the gas constant will depend upon whatever the pressure is being measured in. And so again, I will provide those 3 constants for you on the test. And so you'll just have to know which of those to use then in order to plug in for that. And so I want to go ahead and end this section, and I hope you all have a good rest of your